Uh, so hello everyone. Uh, so we are currently in the fourth. Yeah. So welcome to the fourth week of our Infinity Carry Theory reading seminar. So today, Varun Maladi from Dartmouth College will be a speaker. So Varun, take it away.
Thanks, Marcha. So we're going over 2.1 to 2.3, which is like basically some model category stuff. I feel a little bit awkward because I'm not like an expert or anything. So if there's any questions or you want to embarrass me, like feel free to do that. But the first 2.1 was factorization systems, and mainly a technical section, and 2.2 and 2.3 are kind of the meat of it. But we can start here, and basically this whole model category stuff is really centered on two things, which are lifting properties and weak factorization systems. And somehow this just like this higher category theory structure like falls out from the interplay of these things. But to start with, we have the left and right lifting property, which are the blue arrow I'm drawing here. They're the same diagram. They're just two ways of looking at the same thing. So the left lifting a property is a property that this morphism on the left will have, and the right lifting property is the one that the one on the right will have. And you could say I have a left lifting property against an entire class of morphisms, which means if the right morphism is anything in that class, then I can always find a lift, and vice versa for right lifting properties. Then there's retracts, which is just a technical tool, but I just think of all of this stuff in terms of the category of topological spaces, and it's just an object where you can find this diagram right here, but I just visualize it like how it would look topologically. So we can view morphisms as retracts, in which our graphical intuition maybe isn't the best, but they're just retracts in the category of morphisms. And then you can say like, what does it mean to be stable under retracts? That just means if I were a morphism and if I took the retract of that morphism, if something was a retract of another morphism, then it would also be in that class. Then you could have stability under a lot of other things. You could say F, a morphism, is stable under pushouts if we have like a pushout diagram, and this map F prime is also in your class of morphisms. You could be stable under transfinite completion. And transfinite composition and completion is another technical thing, which I was thinking about writing down and going over, but really like the way I think about it is just this, what it is basically trying to make sense of like infinite strings of compositions of morphisms. So if you're stable under it, that means like, so taking like the transfinite composition, you're like defining a legit morphism that somehow is like representing this infinite composition of morphisms. And to be stable under it just means that legit morphism is also in your class. And saturated is just all three of these things. So yeah, you want these properties to, nice things will happen if one of your classes of morphisms, like right here, this proposition in the book says that like if the class of morphisms which have the left lifting property against F, another class of morphisms, is saturated, then like a bunch of nice things happen, which I just wrote that because it's not too enlightening. I think it's really a technical result that you could look in the book if you wanted to. Okay, and then there's the retract lemma. So here we're saying if F has the left lifting property with respect to P, the screen arrow on the right, then F, and we have this sort of diagram, then F is actually a retract of I. And we have something else on the right here. And again, these are just technical lemmas, which is kind of why I'm breezing through them. I don't think it's super important to spend too much time on them in here, but probably would be useful on your own. And then, okay, we get to one of the main protagonists, which are weak factorization systems. What it basically is two classes of morphisms. So two classes of morphisms make up a weak factorization system, and they have certain interaction with each other. So, well, first of all, they're stable under retracts. We take a retract of something in A or B, we get something in A or B respectively. But second of all, A has the left lifting property against B. And why do we call it factorization? Well, any morphism at all in C must be able to factor through something first in A and then something through B. Okay. So model categories, where does this come up? Well, model categories are basically three classes of morphisms, and certain combination of them, you get two weak factorization systems. Okay, and here's like a extremely prevalent technical argument called the small object argument, which I at least wanted to mention instead of just breezing over because of how prevalent it is. But I mean, it can be stated in quite a bit of generality. And if someone has any better intuition than I do about what this is saying, then I'd be happy to hear it. I kind of was just writing down here a not very general version of it, which is if C is a category with certain nice properties like locally presentable or something, then you take any class of morphisms in C, and then every morphism will factor as a the cell I, and then as a what is this, a retract maybe? Or no, right lifting property. Maybe. Yeah, I think this is right lifting property. Yeah, so if you want a more general category, then you kind of have to relax. You can't just take any class of morphisms. It needs to like satisfy certain conditions, which is the one that they write in the book. But this is the one that kind of comes up in topology. And in that case, this first class of morphisms, cell I, is something like transfinite compositions of pushouts, which somehow are, corresponding to like gluing of cells, and it's useful in that perspective. But yeah, if anyone has any intuition, I'd be happy to hear it. Yeah, so the next corollary, another kind of technical result, which would probably be useful if you're trying to prove that something is a weak factorization system. You can kind of just exhibit certain lifting properties, and you would get kind of automatically that you have a weak factorization system. And here, this is in the category of presheaves. They have a nice example in the book, which was a little bit detailed, but I think it would be good to look over. Okay. So then this next proposition, I kind of think of it in my head as like the compatibility of weak factorization systems with adjunctions. So if you have an adjunction and your one map sends like A, which is one of the classes in your weak factorization systems, and it maps it inside A prime, which is the class from the other category, that can only happen if there's like some sort of symmetry, like the map in the other direction is mapping B prime inside of B. So yeah, some sort of symmetry in like how these play with adjunctions. But okay, I mean, that was a little bit of a technical section, and it kind of was all over the place because really what those were are not really like big picture stuff, maybe just like important tools to have when you're proving a lot of the things here. But we can move to model categories. So, you know, it was only after a few, maybe like a year after learning model categories that I was like really wondering, like, why do we call them model categories? And at least as I understand it now is that model category theory is a specific flavor of one category theory. And the extra morphisms and classes and structure in a model category, just still a one category, are just reflecting or, you know, like shadows of some higher category structure, so to speak. So I guess that's the sense I think of them as models of higher categories. But what are they? Well, they are categories that are locally small. And so we distinguish three classes of morphisms. We have the weak equivalences, what we call fibrations, and what we call cofibrations. And it might be useful here to remember that the weak equivalences are really the things that are important. That's really what we're trying to study, and the fibrations and cofibrations are really more so, again, like just tools to help us understand weak equivalences within the framework of a one category. We care about model categories mostly because of their strict behavior, I think, so we can use them to model stuff. Yeah, exactly. They are one categories. We know how to do one category stuff. And yeah. So we also require that, okay, so these are right now, these are just classes of morphisms. What are the restrictions on them? Well, okay, well, first of all, C needs to have finite limits and colimits. But the first restriction on our classes is that W needs to have this 2 out of 3 property, which this is like a property that says that they behave, you know, kind of like isomorphisms, but they're not as strict as isomorphisms. That's why we kind of call them weak equivalences. And then, okay, and then we have these three need to like make up 2 weak factorization systems. So cofibrations against, I guess, the intersection or of fibrations and weak equivalences, which we call trivial fibrations or acyclic fibrations. That needs to be one weak factorization system, and the other needs to be acyclic cofibrations and fibrations. And so what this really means, importantly, is that we can factor any morphism in a model category as a cofibration followed by an acyclic fibration or an acyclic cofibration followed by a fibration. Okay, and so we say that an object in the category is fibrant if you know, the unique morphism to the final object is a fibration, and similarly cofibrant if the initial object, the unique map from the initial object is a cofibration. And if we think back to what do we really get out of this? Well, if you're a fibrant object, or let's say you're a cofibrant object, so then this is a cofibration. In particular, what do I want to say? Maybe I'll return to this. I want to say
Probably
something
you want to say
about,
something about maps out of X, right?
Yeah, I was thinking more of like cofibrant replacement. So this initial object map here, we could factor it because of our factorization systems as a cofibration followed by an acyclic fibration, and that means that we can find a cofibrant object, which is
Right, the fibrate replacement, fibrate and cofibrant replacement.
Yeah, so we can factor, like if we have some object X, then we could always factor this initial map here where this is a cofibration. So basically what I'm saying is that you can find a object in your model category which is weakly equivalent to your original object, but which is also cofibrant. In the category of chain complexes of abelian groups, I'm pretty sure that this is your cofibrant objects are, or to take a cofibrant replacement like this is the same as taking like a projective resolution of your complex. And to take a fibrant object is to take like an injective resolution of your complex. Yeah, thank you. Yeah, so this is again what I was saying earlier. Weak equivalences are really the core of the theory. Fibrations, cofibrations, these are really just tools. Yeah. So some examples, any category taking your weak equivalences to be literal isomorphisms, but usually why we want to study this at all is because we want to study something that's notably weaker than isomorphisms. Then you have the category of pre-sheaves for any small category. You can actually take your weak equivalences to be all morphisms and your cofibrations to be monomorphisms. Then, like the typical, prototypical, I should say, example of the category of topological spaces. Weak equivalences, weak homotopy equivalents, same homotopy groups between your spaces, fibrations or Serre fibrations, and then you define your cofibrations to here be retracts of relative cell complexes. But oftentimes, you will only really define one of these classes, like fibrations or cofibrations, and then you'll just formally say that the other is, the class of morphisms with lifting against, this other class. Okay, so, taking opposite categories preserves model structure if you just follow where things go. Then also this category, I think is called the over category or slice category or something like that. So how are these three classes related? If a functor does something to one class, do we know what it does to the others? So if we just think about, what a model category is, there's something embedded into the definition that is saying like, these are somehow like intimately connected. Like these are not just three arbitrary classes of objects or morphisms. How are they, sort of connected? Well, the first lemma that addresses this is this really famous lemma called Ken Brown's lemma. It basically says if you have a functor from a model category to a category which has weak equivalences, then you're basically, so he wants to know, do the weak equivalences go to weak equivalences? And he says, if we just take a look at a smaller class of morphisms, we just take a look at the acyclic cofibrations, which are in particular weak equivalences, but a smaller, perhaps, a class, then if those go to weak equivalences, then actually all weak equivalences in C are mapped to weak equivalences in D. But he strengthens it even more and says, okay, we don't need all acyclic cofibrations to be going to weak equivalences. We don't need to check that all of them do. We just need to check that the acyclic cofibrations between cofibrant objects go to weak equivalences. And then somehow magically, like this really controls where the entire class of weak equivalences goes. And it really forces that entire class to go to weak equivalences. Okay, so that's like a pretty useful result, especially in proofs. But so here we come to like the concept of like localization, and at least as I learned it, like the homotopy category. And what it basically is it's forcing your weak equivalences to become isomorphisms. Like again, weak equivalences are not like super like concrete things, I guess, in terms of like constructions. Like a lot of categorical constructions don't play well with weak equivalences. You think maybe if I force these to become isomorphisms, will I be able to then do something in that category and somehow figure something out about the original category? So that's what localization does. It universally takes your weak equivalences to isomorphisms. So first of all, you could show that it will exist. And you can actually kind of strengthen it. So the universal property is initially saying that, that this gamma star is an equivalence of categories, but you can actually construct the homotopy category in such a way that it's actually an isomorphism of categories. So, how would you construct it? So you kind of have these maps going in both directions that I tried to draw. You have these like backward green maps. And, I was thinking about this, and the way I think about it now is just we're kind of formally pretending that those green maps are invertible. And that's kind of how we're defining the homotopy category. We're pretending like they could go in the other direction. Okay, so then we have some constructions in model categories that will help us in the future. The first is a cylinder. This is probably best thought of like using some topological intuition. This is the categorical definition. So this is a notation they use here, IA. In the category of topological spaces, I would be the unit interval, and your cylinder object would just be, like A cross I. It would just be, if it was S1, S1 cross I would literally be a cylinder. Okay, so then dually you have your co-cylinder, which is, again, if you were thinking about this topologically, this would be the path space. I attempted to draw a path space and realized it was probably not very instructive. Yeah. So then we can define left homotopy, which is the homotopy. When we think maps are homotopic, we learned that in algebraic topology. We're talking about left homotopy. It's this diagram. So it's saying, if I were to map my object into the cylinder object and then out again, I don't know how to describe this. It's this diagram here. But if you were to look at like what a cylinder object is, and these are your two objects, your two copies of your initial object, then what this is basically saying is that like I is representing, your continuous deformation. And if you're able to put them both into your cylinder object and then continuously deform, of course, we're talking in the context of topology here, but continuously deform your cylinder into whatever you want, then that would mean that there's some, like those two maps are homotopic is kind of what it means in topology. So, you could define the right homotopy. It would just be kind of like a diagram in the opposite direction using your co-cylinder instead of your cylinder. And well, in the case where your object A is cofibrant and X is fibrant here, these notions are actually the same. Yeah. Okay, so then this is the first week homework assignment of every person in algebraic topology, showing that this is an equivalence relation. Of course, it's a little bit more general here, but basically they're saying that, it's an equivalence relation. And if you define this thing here that takes an object, another object, and takes their humps, and under this equivalence relation of left homotopy, you define this sort of, bifunctor kind of, you define this sort of functor. Okay, so the next theorem is pretty cool in my opinion, saying that the homotopy category, which was, the category, there's this universal functor sending C to, like universally forcing your weak equivalences to become isomorphisms. So your homotopy category of your cofibrant objects is not exactly, it's equivalent to the homotopy category of your original category. And similarly for fibrant objects. So what is it saying? It's saying that somehow, we defined a model category. We had this interaction between these classes of morphisms, cofibrations, fibrations, and weak equivalences. And from that, we were able to define cofibrant objects and fibrant objects. And because of like the way we set it up, somehow our cofibrant objects and our fibrant objects are kind of reflecting the weak equivalence structure of the entire category as a whole. So we can extend this functor here, which was kind of taking the Hom sets under between cofibrant objects and fibrant objects under left/right homotopy, and we can upgrade it to we're acting on the homotopy categories. And then we have this theorem, which is quite cool also, which is saying that, we defined this Hom set was modulo left homotopy. And then here in the homotopy category, we have, the Hom set mod weak equivalences. And this theorem is saying that, again, the object on the left has to be cofibrant, the object on the right has to be fibrant. But in this case, these Hom sets actually agree. So left homotopy is really encapsulating weak equivalences, or even the other way around. So, we defined the homotopy category with weak equivalences. We could just define this other category to be objects which are fibrant and cofibrant at the same time, and their maps between them are the normal maps, but up to left homotopy. And then this corollary is kind of reflecting what I was saying above, but it's saying that this category is canonically equivalent to the homotopy category. again, left equivalence is, playing the role. Left homotopy equivalence between cofibrant fibrant objects is highly reflective of the relationship between all objects and weak equivalences between all objects. So as a summary, these three categories are all equivalent to the homotopy category. Cool. So the last section was on derived functors, and this is like our technique for normal categorical constructions not playing well with the higher category structure. So, like for example, like even like limits and colimits are not necessarily preserved under homotopy. So, like if we just take an example from topology. So if we have like this colimit, this is just attaching two n-dimensional disks along their boundary. You would get a sphere of one dimension higher. But these disks are obviously homotopic to a point, but well, you don't need to write it out, but yeah, these are not. This is not SM. So colimits, limits, they don't play well with homotopy. And what do we do about that? Well, we can sort of derive it. And that comes to the topic of derived functors. How compatible are functors with localization is the first question we could ask. And anytime you see the setup of a question is like saying, oh, we have this functor from here to here. Oh, and we also have a functor from the domain category to somewhere else. Can we sort of extend the initial functor, approximate it somehow to this other category? The general tool for that is con extensions. So that's what we'll do here. Going forward, we will talk about model categories. I won't always write it down, but we can assume that some model categories unless I say otherwise. But okay, we have a model category, we have localization, and let's say we have a functor between model categories. We can form what is called the left-derived functor. So what's happening here? We are wanting to extend this functor from C to D to a functor from the homotopy category to D. We want to see like what happens to this functor if we pass to the homotopy category in the domain, if we localize the domain. Okay, so we can kind of formally do this. This is the general theory of con extensions. Left-derived functors are annoyingly right con extensions, and right-derived functors are left con extensions. So what do we achieve? The left-derived functor of a functor is a map from the homotopy category to D. Do these exist? Well, there's general theory on the existence of con extensions. So, I would risk saying usually yes, but yeah, there is some general theory that you could check. But what do they look like? And in the situation of Ken-Brown's lemma, so we had a model category, C, and D was only required there to be a category with weak equivalences, but let's just say D is a model category as well. The situation of Ken-Brown's lemma just means that what, like cofibration, or no, acyclic cofibrations between cofibrant objects are sent to equivalences. And then we get that weak equivalences and weak equivalences. Yeah. So by the universal property, we get this functor FC. So what is this functor? Okay, it's the homotopy category of the category of cofibrant objects mapping to D. Why does this exist? Well, because cofibrant objects, so acyclic cofibrations between cofibrant objects, which become isomorphisms in the homotopy category, are sent to D. Let's keep reading and we'll see what happens. Okay, so for each X in your category, make your cofibrant resolution, which was what I was describing earlier. And so what is taking the cofibrant resolution? That's like a map that takes an object in C and gives you something in D, it gives you a cofibrant object. So this kind of induces, you have to show it induces a map from the homotopy category of C to the homotopy category of your cofibrant objects. And you can define your left-derived functor as follows here. And okay, so what was the point of this? This was just saying that in the situation of Ken-Brown's lemma, your left-derived functor exists, first of all, and that you can actually like quite explicitly describe it. Yeah, so that was proposition 2.3.3. In the same situation, if you have any functor, okay, so this is this is like the general theory of like composing with your functor on top. You can somehow extend your left con extension if it existed initially. So here it just tells us if you had a left con extension and then you try to extend the original functor, compose it with another functor, you could also get another left derived functor. Okay, so your left derived functors were functors from the homotopy category of C to D. But what about the homotopy category of C to the homotopy category of D? And that's where total derived functors come into the picture. Basically, these are the total derived functor of F is just a regular left derived functor of F, doing F first and then gamma prime. Yeah, so it's basically, we had the situation above, like, we're just kind of extending by now like localization. So that D would go here to like the homotopy category. And, general theory tells us we still have a left derived functor. So we have left derived functors, and then we have total derived functors, which are between homotopy categories. And these behave pretty well. This proposition, I guess, is again it's just a kind of a technical benefit. You have this kind of like homomorphism property, I guess, where you can take the derived functor of the composition, total derived functor of the composition of two functors, or take the total derived functor and then compose them. Okay, so what do adjunctions look like? I think this is a logical next step. Con extensions kind of subsume the theory of adjunctions and the theory of a lot of things, I suppose. But so what do adjunctions look like on the level of localizations? If we had an adjunction and we localized it, so now it's not between C and D, it's between the homotopy categories, do we still have an adjunction? Generally, the answer is no. But when we do have it, we call them Quillen adjunctions. These are just adjunctions between model categories that descend to adjunctions on the homotopy categories. Okay, so when do we have Quillen adjunctions? When do we know that an adjunction descends to an adjunction on the homotopy category? Well, if, okay, we got this adjunction above, if F preserves cofibrations, G preserves fibrations, then we have a Quillen adjunction. Okay, so then there's this remark, which I was kind of thinking of in my head as the sort of duality between fibrations and cofibrations across the adjunctions. So let's say you have a Quillen adjunction and your F preserves cofibrations and acyclic cofibrations. So it sends cofibrations to cofibrations and also acyclic cofibrations to acyclic cofibrations. That only happens if G in the other direction preserves fibrations and acyclic fibrations. And actually, I misspoke a little bit earlier. Either of those conditions is equivalent to the condition that F and G are Quillen adjunctions. So sort of, if one of these functors preserves seemingly like half of the model category theory structure, then the adjunction kind of fills in the rest, and you get that your adjunction actually descends to the homotopy category. So again, what was the point of all of this? The point was that, we want to derive useful functors to hopefully get like a homotopy theory analog of useful functors. And for example, like the limit functor, we want to know, if I was showing before, limits, colimits not really preserved, but maybe we can find some analog. Okay, there's this thing that comes up a bit from this point on, and these are projective model structures. If it exists, then it's the model structure such that your map is it's a projective model structure, let's say on this CI, which was just the functors from I to C. If it exists, then a functor is a fibration if, kind of object-wise, it's a fibration. They don't necessarily have to exist. When do they exist? Okay, here's a bunch of examples when they do exist. Error categories, small discrete categories, condition on C and I. Yeah. So projective model structure. Oh, and what I was trying to say here earlier is, so projective resolution is the cofibrant replacement of an object with respect to the projective model structure on chain complexes. So on chain complexes, you have both a projective model structure and an injective model structure, and these respectively define projective resolutions and injective resolution. Okay. So if we're working in a projective model structure, then some nice things happen with limits and colimits. So if you have this projective model structure, again, you're working in the functor category from I to C. C has I index colimits, and let's say you have a cofibrant map in your projective model structure, which is like a natural transformation. If object-wise, this is a weak equivalence in C, then your I-index colimits will be a weak equivalence. So, this map from X to Y induces a map from the colimits X, these sort of colimits, because these are both functors, these are actually objects in C, and they are weak equivalent if the conditions above are true. So this is saying something like when two objects in your category or limits are colimits, I-index colimits, and they are weakly equivalent when these conditions are true. So this had a lot of specific cases, and these are the corollaries in the book that I didn't write down specifically. Yeah, okay. But here's one of the big ideas is that of homotopy colimits and homotopy limits. If anyone has like a concrete example they can think of, I'd be happy to hear it. But basically what's happening is we would say X is a homotopy colimit if, okay, so first we are taking the total derived functor of the I-index colimit functor. So what is this limit colimit functor? It takes a functor from I to C, and it spits out an object in C. The total derived functor descends this to the level of the homotopy categories. So what are we saying? We're saying that we're calling this functor like the homotopy colimit, and the homotopy colimit of F may or may not coincide with the regular colimit of F. So this can happen in certain cases that the ordinary colimit and the homotopy colimit coincide. For example, if C has I-index colimits, projective model structure, and F is cofibrant, then yeah, those two will agree. A specific instance of these homotopy limits, colimits are, so again, I'm just talking about colimits, but you can dually define limits. Here we have like homotopy pushouts, and the book calls them homotopy co-Cartesians, referring to the square as a whole. This is just saying, Y prime is the homotopy colimit of this diagram. So it's like the homotopy pushout. Another example of regular and homotopy colimits coinciding is that if a pushout is between cofibrant objects, so every object here is cofibrant, every map is a cofibration, then and your initial diagram was also a pushout in the normal one category theory sense, then it will also be a homotopy pushout. And like you can imagine like dual statements for pullbacks and vibrations and fibrant objects. Okay, so I mean, here's another example. You have any commutative square and your top and bottom maps are weak equivalences, then this will actually be homotopy co-Cartesian. And if in the above square is co-Cartesian in the one category sense, it's a normal pushout. F is a cofibration, your top two objects are cofibrant, then you're homotopy co-Cartesian. So basically, everything in the book after the section on what homotopy limits and colimits are were kind of specific cases of it that mean that you can, like when is it allowable to compute limits normally in like a homotopy category, like something, there's some, maybe that's one way to think about it. Yeah, and that was pretty much it. I would say the most important things in the section were homotopy, limits, colimits, and yeah, I think that's the real protagonist here. And then, just general model category stuff to really, I would really recommend, if you want to learn more about this, just to go to the NLab page, the Introduction to Homotopy Theory. I think it does a much better job. Obviously, this book is stating it in full generality, but might be nice to, kind of see where the theory comes from. But, yeah.
So let's thank Varun for